So we did the examples 1 through 4 on page 1 yesterday. So you flip over your paper. We'll take a look at example 5. Alright, and so let's just review the 4 steps in solving problems of this nature. Word problems, okay? Step number 1, draw a good picture. Because a good picture can go a long way in helping to understand a problem. Number 2, define the variables. Right? What does X represent? What does Y represent? What does Z represent? So forth. Okay. Number 3, set up the equation, which is just a mathematical model, right, describing the problem. And then number 4 is solve the equation. Solving the equation should give you the solution to the problem. Okay. And so we're mostly focused on 1, 2, and 3. Okay. Number 4, right, is reserved for calculus. Difficult. Okay. All right, so let's look at example 4. A farmer with 700 feet of fencing wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle. What is the largest possible total area of the 4 pens? Okay. So let's draw a good picture, step number 1. So we have a rectangular piece of land, okay? But we don't have a rectangular piece of land. The farmer has 750 feet of fencing, and he wants to use that to enclose a rectangular piece of land, okay? But he wants the rectangle to be a maximum size, okay? So we have 700 feet of fencing, and he wants to enclose a rectangular area, and then divide it into 4 pens. Okay. So let's do like we did yesterday, right? We'll let X be the width of the land area, okay, the rectangular area, and we'll let Y be the length. So X is equal to width, and Y is equal to the length of the rectangular area. Okay. But he also wants to divide this rectangular area into 4 pens. Okay. So there's 1 pen, there's a 2nd pen, here's the 3rd pen, and the 4th pen. Okay. So some of that fencing is going to be used to divide this rectangular area into 1, 2, 3, 4 pens. Okay. Well, this section of fencing is X feet long, right? Same as the width of the area, rectangular area. This fencing is X feet long. This fencing is X feet long. Okay. So in dividing this rectangular area into 4 pens, okay, we have 4 sections of, well, we have actually 1, 2, 3, 4, 5 sections of fencing X feet long, and 2 sections of fencing Y feet long. Okay. Well, we're given 750 feet of fencing, so the total fencing, right? Total fencing here has to equal 750 feet. So there are 5 sections of fencing X feet long, right? So 5X represents those 5 sections of fencing, and then there are 2 sections of fencing Y feet long. So 2 times Y represents the total length of that fencing. Okay. And so these 5 sections of fencing X feet long and the 2 sections of fencing Y feet long have to sum to 750 feet, because that's all the fencing that we have. And so this is the fencing constraint. So that's a linear equation, actually, and we can solve for y. Okay. And so when we solve for y, right, we can write the length of the rectangle y, okay, as a function of the width x. And so we subtract 5x from both sides. We have 2y is equal to 750. Minus 5x. And then we divide both sides by 2. And we get y, the length of the rectangle. We can divide 750 by 2 and 5x by 2. And we get 300y, the length of the rectangle, is equal to 375 minus 5 halves x. So whatever the width is, the length is going to be equal, the length y is going to be equal to 375 minus 5 halves times the width. Okay. All right. Now we want to maximize the area of this rectangular piece of land. Well, area is equal to width times length. Well, in this case, the width is represented by the variable x, and the length is represented by the variable y. But y, with the fencing constraint, we're able to write y as a function of x. So we can replace y over here with 375 minus 5 halves x. So when we do that, we have the area is now written as a function of x, the width. But now I can distribute the x inside the parentheses, and I have f of x is equal to 375x minus 5 halves x squared. What kind of a function is this? Yeah, it's a quadratic function, right? And its graph is a parabola. Okay. So to maximize the area, right? Well, let's just notice something here about the coefficients in this quadratic function. Okay. So let's make a note. This is a quadratic function. Okay. The coefficient a in front of the x squared is minus 5 halves. The coefficient in front of the x, b, is 375. And the constant c is 0. So because a is negative, you know the graph is a parabola that opens down. So this quadratic function has a maximum. This is the vertex, right? The x coordinate for the vertex gives you the optimal width of the rectangular piece of land. And the value of the quadratic function at x, right, the y coordinate, gives you the maximum area that you can get with that 750 feet of fencing. Okay, so x gives you the maximum width, and the value of the function gives you the maximum area. Okay, its area is a function of the width x. Okay, so define the x coordinate for the vertex. We know how to do that, right? That's exam 2 material. X is equal to negative b over 2a, and negative b is minus 375, and 2 times a is 2 times minus 5 halves. So this is equal to minus 375 over negative 5, which is equal to 75. So x equals 75 feet is the optimal width. Of the rectangular piece of land. Okay. So each of these 5 sections of fencing are 75 feet long. Now the optimal length y is equal to from this constraint over here, we put in 75 for x, and we get the optimal length for the rectangular piece of land. Y is equal to 375 minus 5 halves x. And so we put in 75 in for x to get the optimal length. So y is equal to 375 minus 5 halves times 75. And when you do PEMDAS, right, order of operations, you get the optimal length is 187.5 feet. That's the optimal length. Okay. So the question is, what is the largest possible total area of the 4 pins? Well, area is, right, width times length. Which is x times y. Okay. What is x? X is 75. Y is 187.5. Now this is where you need a calculator. Okay. On exam, you'll have nicer numbers to work with. Okay. And we do 75 times 187.5. You get the maximum area. For the rectangular piece of land is equal to 14,062.5 square feet, or feet square, however you guys like to say it. We used to say square feet, but I know students often say feet square. Okay. So given 750 feet of fencing, with a rectangular piece of land divided into four pins, okay, the largest rectangular piece of land that you can fence off with that 750 feet of fencing is 14,062.5 62.5 square feet. Okay. That's the largest rectangular piece of land you can fence all with that 700 round. Okay. Any questions on that, ladies and gentlemen? Okay. Well, example 6 is similar to example 5. We have a rectangular plot of land. A rectangular plot of land will be fenced into 3 equal portions by 2 dividing fences parallel to 2 sides. The area to be enclosed is 1,000 meters squared. So in this case, it's the area that's fixed. Okay, not the perimeter, not the amount of fencing. Okay. Express the total amount of fence as a function of the width x that we require to build this lot. So again, let's start off with a good picture. And again, the width is x, the length is y. Okay. But now we're going to divide this rectangular piece of land, right, into 3 equal pins. And technically, so each of these 2 sections of fencing, right, are x feet long. Yeah. And technically speaking, the width of each of these pins is 1/3 the length. The length is y. It really doesn't matter whether the pins are of equal size or not. Okay. All right. So again, the area of the rectangular piece of land is width times length. Well, the area is fixed at 1,000 square feet, or 1,000 square meters, excuse me. And width is x and length is y. And so, solving for y, we get whatever x is, y has to equal 1,000 divided by x. Okay. Whatever x is, y has to equal 1,000 divided by x in order for the area of that rectangular plot to be 1,000 meters squared. Okay. So this is the area constraint. All right. So what's the total amount of fencing needed? Well, we have 4 sections of fencing x meters long and 2 sections of fencing y meters long, right? So the total amount of fencing required is 4 times x plus 2 times y. And so, actually I'm going to write this, flip the 2 sides, I'm sorry. So the total fencing required is 4 sections x feet long and 2 sections y, excuse me, I said feet, I meant meters, y meters long, x meters long and y meters. So if I replace y with 1,000 over x, then the total amount of fencing, right, is now written as a function of x, the width of the rectangular plot. So we have f of x is equal to 4 times x plus 2 times 1,000 over x. And so the total amount of fencing needed as a function of the width of the rectangular plot is equal to 4x plus 2,000 over x. Any questions on that, right? So that was, right, we were instructed to express the total amount of fence as a function of the width x that we required to build this lot. And that's what we've done. Okay. Now, to find the optimal amount of fence, we gotta do some calculus. Okay. So you notice it's not a quadratic function where we can just look for the vertex. Okay. Somebody's starting to raise their hand. Love it, so, no. Okay. All right, so any questions on this, ladies and gentlemen? All right, example, flip over your paper. Example number 7. A wooden rectangular box with a square base of length x and height h is to have a volume of 32,000 cubic centimeters. Okay, so the volume is fixed. You know, volume is length times width times height. Okay. Express the amount of wood required to make the box as a function of length of a side of the base of the box. Okay. So, we all know what a box looks like. And how much you can put in a box is the volume. Alright, so this box that we're building has a square base. So hopefully I'm drawing a good square. Okay. And, right, so this is the bottom, right, or the base of the box. And it has a square bottom. So all 4 sides, right, of the bottom of the box are the same length. And you know, boxes have 4 sides. So this is what one side of the box looks like. Okay. And it has an open top. Okay, there's no lid. And so for each of the 4 sides of the box, the width will be x centimeters, right? Because the bottom of the box, right, is square, x by x. And the height of the box, right, the height of one side is h centimeters. So that's a visual of the bottom of the box and one of the 4 sides of the box. Okay. All right. Well, the volume of the box, right, is width times length times height. Well, width and length are the same. Right? Width times length are the same when the bottom of the box is square. Okay. Square shape. And then we have the height of the box, which is different. So the length is x and the height is h, right? So the volume of the box is x times h. And the volume of the box is fixed 32,000 cubic centimeters. So volume of 32,000 cubic centimeters is equal to the length squared times the height h. And now if we divide both sides by x squared, we have the height as a function of the length x. So h is equal to 32,000 over x squared. So this is based on the volume constraint. The volume of the box is constrained to be equal to 32,000 cubic centimeters. Okay. All right. Now, we got to express the amount of wood required to make the box as a function of length of side of the base. Okay. Well, the amount of wood is equal to the area of the four sides of the box and the bottom of the box. Right. That gives us the amount of the wood. We're not concerned about the thickness. We're just concerned about, right, the dimensions of the wood. Okay. So what's the total amount of wood? Right, length times width that is required to build the bottom of the box and the four sides of the box. Okay. Well, the area of the base is width times length, which is just because it's square, it's length times length, which is equal to x squared. Okay. So that's the amount of wood required to build the base of the box, right? X squared centimeters. Okay. X squared centimeters squared. The area of one side of the box, there are four sides. Is height times width, right? Height is h, width is x, okay? You can see that over here, right? So the amount of wood to do one side, right? Height times width is h times x. So the total area of the four sides of the box plus the bottom of the box is x squared for the bottom of the box, and then 4 times h times x for the four sides. Okay. So we have the bottom plus four sides. That's the total area for the bottom plus the four sides of the box. Okay. Well, if we replace h with what it's equal to based on the volume constraint, h is equal to 32,000 over x squared, you now can write the total area, okay, the total amount of wood needed to build the box as a function of x, right? The length of one side of the base, the bottom of the box. So we're using S of x for total area. So S of x is equal to x squared plus 4 times h, which is 32,000 over x squared times x. Okay. So all I did is replace total area with S of x, right? That's what we're using for area in this problem. And replace h with 32,000 over x squared, right, due to the volume constraint. Okay. And now we simplify. Total amount of wood needed to build this box is equal to x squared plus, now, 4, same as 4 over 1. So 4 times 32,000 is 128,000. And x, right? X squared, same as x times x. So one of the x's in the denominator cancels with that x, and we're just left with one x in the denominator. And so this is the total amount of wood needed to build the box with a volume constraint of 32,000 cubic centimeters. Okay. The amount of wood needed written as a function of the width or length of one side of the bottom of the box, the base of the box. Now to find the optimal length, you got to use calculus. Any questions on this? So this is the area of the bottom of the box plus the area of the four sides of the box. Okay. And the reason the area of the four sides of the box is like this is due to the volume constraint of 32,000 cubic centimeters. Any questions on this, ladies and gentlemen? Okay. All right, one more and you'll have everything you need for the web assigned homework. So example 8 at the bottom of the page. An open box having a square base is to be constructed from 108 square inches of material. So here we had a volume constraint. In this problem, it's not volume that's constrained, it's the amount of material we have to make the box. Okay. What dimensions should be used for the box to obtain a maximum volume? Okay. So this problem has the same pictures. Right, the bottom of the box has a square base, x by x, okay, and the area of one side of the box is h times x, right, where h is the height of the box. Okay. So x is length or width, and h is height. All right. Well, we're going to borrow this equation from the previous example. The total area of the four sides of the box plus the bottom of the box, right? That's the amount of material we need. That total area is the area of the bottom of the box plus the area of the four sides of the box. Right? I'm borrowing this equation from the previous problem. Right? That's the total area of the bottom of the box plus the four sides. Okay? All right. Well, we're given that we have 108 square inches of material to build this box, right? So that's the total area. The total area is constrained to 108 square inches. And that's equal to x squared plus 4hx, okay? So we could call this the material constraint. And now we can solve for h and write the height of the box as a function of the width or the length of each side of the bottom of the box. And so we subtract x squared from both sides. And then we divide both sides by 4x, right? Divide both sides by 4 and x. get the height h is equal to 108 minus x squared over 4x. So, I switched the two sides of the equation, divided both sides by 4, and divided both sides by x, 4x. So the height, given our material constraint of 108 squared is a material, this is the height constraint, right? As a function of the width or length of each side of the box. Well, we want to maximize the volume. So volume for this box is length times height, right? Because remember, it has a square base. So the volume in this case is equal to x times x times 108 minus x squared over 4. Well, you know x times x is x squared. You know what? I forgot something. There should be a 4x in the denominator, right? Didn't think that looked right. Okay. Yeah, so the height is 108 minus x squared over 4x. And so I just rewrote x times x as x squared over 1. And now when you multiply two quotients, right, you multiply straight across, and you get this case. The volume is equal to x squared times 108 minus x squared over 4x. Okay. So the volume is now a function of x, right? One of these, right? X squared is x. I should maybe could have left this x times x, then you would see x in the numerator and x in the denominator cancel. And we're left with x times 108 minus x squared over 4. So that is the volume of the box written as a function of the length of one side of the base. Okay. It matters how big the bottom of the box is, right? That affects the volume. So there's a length, an optimal length for the bottom of the box that maximizes the volume. Okay. And so you would use calculus now at this stage. If you know, you might notice that if you distribute the x inside parentheses, you get x cubed. Right? That's so this is a polynomial of degree 3, and we don't have tools at this stage for calculus to find the optimal value, right, for a third degree polynomial, but you will in calculus. So this is the volume written as a function of the length of one side of the base. Okay. Any questions on that, ladies and gentlemen? Okay. So you have everything you need to successfully complete the web sign homework. All right, so section 2.10 is titled the tangent line problem. And so you're going to get a taste of calculus in this section. So then we get, but we're not gonna delve into it. You're just gonna get a taste, okay? For those of you that take math at 120. So let's just do a little review here. Coordinate plane and here's the graph of the straight line, right? You know that the steepness of the line or the slope of the line is the same at every point on the line, right? So to find the steepness or the slope at every point on the line, you only need 2 points on the line. You calculate rise over run, and that gives you the slope at every point on the line. Well, in calculus, we're interested in the problem. What about for like a smooth curve, like a polynomial? How do you calculate the steepness or the slope at each point on that curve, on that graph? Down here, okay, I'd like to look at graphs as the sides of hills. So if this is the side of a hill over here, and I start walking right from the left to the right, I'm walking up this hill and it's the same steepness everywhere, right? Doesn't get more steeper and less steeper. The steepness stays the same. But over here, when I start walking here on the left, right, it's pretty steep going uphill, and then I get to the top of the hill and it's pretty flat, okay? And then I start walking downhill, and the further I walk downhill, the steeper it gets until I get to the bottom of the hill where it's pretty flat. And then as I keep walking, right, walking uphill, it gets steeper and steeper, okay? So how do you calculate the slope or the steepness on a graph like that, at each point on a graph like this? Okay, that's what calculus is concerned with. Okay. Well, we know how to do that. We know how to calculate the slope or the steepness at each point on a graph of a curve like this. And one thing we need to do that is what is called the difference quotient. Okay. Now I have taught college algebra. So those of you who took college algebra, I'm assuming that you had an introduction to the difference quotient. I can't remember if I saw this in my high school algebra or not, to be honest with you. I can't remember. Okay. But the difference quotient given a function f of x is equal to the function f evaluated at x plus h minus the function itself divided by h. That's called the difference quotient. Okay. Back in section 1.5, we learned how to reduce simplified various algebraic expressions. So we're kind of going to be doing that here with the difference quotient. Okay. So let's calculate on page 1. We're going to calculate the difference quotient for a couple of different functions. And then we're going to learn how to find the slope or the steepness at each point on the curve using the difference quotient. Okay. So in the first problem, example 1, f of x is a quadratic function, right? F of x is equal to 4x squared minus 2x plus 9. And so the steps are broken down for you. First, we're going to evaluate the function f of x at x plus h. Then we're going to subtract f of x from that result. And then we're going to divide this result by h to get the difference quotient. Okay. So to evaluate f of x plus h, we just put in x plus h on the right hand side of f of x wherever we see an x, right? And so when we do that, we have 4 times x plus h squared minus 2 times x plus h plus 9. Okay. Well, distributing the minus 2 inside parentheses is not difficult, but you do have to FOIL x plus h squared. Okay. So let's just review on the side here what we mean by x plus h squared. Let me tell you what it does not equal. It does not equal, and people do this on exams, this does not equal x squared plus h squared. Because when you FOIL, you got the inner and the outer terms. Okay? And people miss that when they do that. Okay? So, x plus h squared is 2 factors of x plus h, right? That's what squaring means, right? You multiply something by itself. Well, now, when you FOIL, you multiply first terms, you have x times x, which is x squared. And then when you multiply outer terms, you have x times h, or h times x. Then when you do the inner terms, you have h times x. And when you do the last terms, you have h times h, which is h squared. F-O-I-L. And you have the 2 like terms, hx plus hx, which is 2hx. That's why x plus h squared is not equal to x squared plus h squared. Because the outer and the inner terms, you add them together, you get 2hx. So, over here, x plus h squared is equal to x squared plus 2hx plus h squared. And I'm just going straight across on my paper because I notice you don't have a lot of room between A and B. Okay. And now, when we distribute the minus 2 inside the parentheses here, we have minus 2x minus 2h, and then plus 9. And then lastly, you have to distribute the 4 inside parentheses here. And you have 4x squared plus 8hx, right? So 4 times x squared is 4x squared. 4 times 2 is 8, so we have 8hx. And then 4 times h squared. And then minus 2x minus 2h plus 9. And you'll notice those 6 terms, we have no like terms. Okay. Alrighty? So now the next step in B, we have to subtract from f of x plus h, f of x. And so we have all that in a rectangle, 4x squared plus 8hx plus 4h squared minus 2x minus 2h plus 9. And now we're going to subtract f of x from that. And when you subtract f of x, put it in parentheses. Because if you don't, you'll subtract the first term, not the second, third term, and you'll be off. So we have in parentheses 4x squared minus 2x plus 9. And now to simplify, right, you gotta distribute the minus sign inside the parentheses. And we have 4x squared plus 8hx plus 4h squared minus 2x minus 2h plus 9 minus 4x squared plus 2x minus 9. Alright, when you subtract the function, you subtract f of x, it changes the sign of each of those terms. And now you can see we have 4x squared minus 4x squared minus 2x plus 2x, 9 minus 9. And now f of x plus h minus f of x is just equal to 3 terms. Okay. It's equal to 8hx plus 4h squared minus 2h. Any questions so far? So you get, in calculus, you gotta have really good algebra skills, right? Because we do stuff like more complicated algebra than this, right? That's why it's very important to develop your algebra skills before you take Math 120. All right, so step C, divide our result in part B by H. So we have f of x plus h minus f of x over h is equal to 8hx plus 4h squared minus 2h over h. Division, remember fraction bars are like division symbols. Division does not undo addition or subtraction. So each of these terms have to be divided by h. So this is equal to 8hx over h plus 4h squared over h minus 2h over h. Well, in the first quotient, you see h is canceled. We're left with 8x. In the second quotient, this h cancels out one of the h's in the numerator. Right? H squared over h is just h. So we have plus 4h. And then in the third quotient, h is canceled, and we're left with minus 2. So this is the difference quotient for this quadratic function, 4x squared minus 2x plus 9. Any questions on that? On the algebra? Okay. So let's take a look at example 2. We have f of x is equal to square root of x plus 1 minus 3. So, part A, find f of x plus h. So again, wherever you see an x on the right-hand side of f of x, you replace it with x plus h. So when I replace this x with x plus h, I have the square root of x plus h plus 1, and then we're minus 3. Remember, the minus 3 does not go under the radical. Step in B, we got to subtract from f of x plus h f of x. So we have the square root of x plus h plus 1 minus 3. And remember, when you subtract f of x, it has this, f of x has two terms in it. If f of x has more than one term, right, 2 or more terms, put it in parentheses, or you'll only subtract the first term and not the second, third, fourth, fifth, sixth terms. So it's minus the square root of x plus 1 minus 3 in parentheses. So now we distribute the minus sign, which is the same as multiplying by minus 1. And we have x plus h minus f of x is equal to the square root of x plus h plus 1 minus 3 minus the square root of x plus 1 plus 3. Multiplying, distribute the minus sign, same as multiplying all the terms by minus 1. But now you can see minus 3 plus 3 cancel, right? That's equal to 0. And we're left with f of x plus h minus f of x is equal to the square root of x plus h plus 1 minus the square root of x plus 1. So that's f of x plus h minus f of x. And now to get the difference quotient, we divide that by h. So when we divide the right-hand side by h, we have the square root of x plus h plus 1 minus the square root of x plus 1 over h. That's the difference quotient for this function f of x equals square root of x plus 1 minus 3. Now riddle me this, ladies and gentlemen. If we have to rationalize the numerator, we did this in section 1.5, right? We learned how to rationalize the numerator, how to rationalize the denominator. Do you remember how we rationalize the numerator? What do we have to multiply top and bottom by? Not the reciprocal. Conjugate. Conjugate. Who said that? Yeah. Conjugate, right? In the conjugate of the numerator, you just change the minus sign to a plus sign, right? We're going to review that tomorrow on a different problem. Okay? Yeah. So it's a good recall. Okay? Yeah. If we were going to rationalize the numerator, we'd have to multiply top and bottom by this square root plus that square root. Okay. All right.